All right, so today we're going to be looking at glass evidence. Um, and glass evidence, just like soil evidence, is going to be considered class evidence because there's a lot of it that is going to be around. It's just so prevalent. There's not a whole lot of specific materials um, that are made with certain glasses. So glass is a very common material in our environment. You're going to find it in different things like windows, bottles, headlights, glasses. And a lot of times the same materials are used, so it's very hard to tell them apart from one another. Investigators can use glass fragments at a crime scene to place the suspect at the crime scene. Um, Now, if they just find the same type of glass, it's harder to kind of have a concrete link that that suspect was at the crime scene. Um, but it can still be used as class evidence along with other class evidence against that suspect. Glass fragments can be found in places like shoes, whether it falls into the shoe, whether it gets embedded in the sole of the shoe, um, clothing, any type of fold in clothing or cuff in jeans, things like that can collect glass. It can even be embedded within skin as a result of breaking a window or getting hit by a car. So they can find those fragments and match it up to a source um, if the glass is definitive or has definitive characters. So glass can be considered class individual evidence. So most glass is class evidence. It can be individualized if it can be pieced back together like a puzzle. So if they are able to take the glass fragments and they can match up all of the edges to reframe that piece of glass or whatever they had, that glass can be considered individual evidence because they can match it up to a unique source. However, glass tends to shatter so much, it tends to break into these tiny little pieces that it's almost impossible to piece together. So most often glass is referred to as class evidence. The only way it can be considered individual evidence if you're able to piece it back together like a puzzle. And glass can be linked to a suspect or crime scene by looking to see if it's the same type of glass or if it has the same properties. So we can look at the physical properties of glass, and if enough physical properties match, we can kind of confirm that yes, this is the same type of glass that is found at the crime scene. So we might notice if the glass has an odor. A lot of times this may give us a clue of what was within that glass container. So if we have a glass bottle that had soda in it, it might still have that kind of sweet sugary smell from the soda. If someone had glass that had an alcohol in it, it might still have the odor of that alcohol. We can look at the color of the glass or how clear it is. We can look at the melting point or boiling point of the glass. It's more likely to find the melting point. The boiling point is going to be very high for us. We can look at the glass's density, its refractive index, so remember its ability to bend light or allow light to go through it. And we can also look at fracture patterns of the glass. Depending on what the glass is made of or where the impact to glass would be, it's going to show different fracture patterns that we can match up. So looking at glass, glass is a hard amorphous material that's usually transparent, composed of silica, which is that silicon dioxide, and other element oxides. So that silica or sand tends to be one of the primary materials that is used to make up glass. They will add other materials to change the properties or color of glass. What we mean whenever we say glass is an amorphous material. An amorphous material has a non-crystalline pattern with atoms or units that are arranged randomly. This is what gives it that strange fracture pattern where it will break in a lot of different directions. So if you look at this image in the bottom left, whenever we look at solids, usually all of the atoms are nicely arranged in like rows and columns, and it's a repeating pattern. Whereas with glass, that amorphous material, the atoms are not necessarily all in nice rows and columns. It's more of a random pattern. There's bigger gaps that you'll notice between atoms. And so it will fracture along these different planes within the glass itself. And glass is brittle, so it does break very easily. And whenever it does break, it shows a conchoidal fracture pattern or a circular pattern. So you'll notice kind of it will break in like arcs where it'll look like you have a rainbow pattern within that material. So it will be more circular like a seashell. So here on the left, we have a piece of glass that if you look, it is broken on different planes, but each plane you can kind of see those arcs, those rainbows on each of those broken surfaces. Right, and glass is not all the same. So there are different types of glass or families of glass that we come across based on its chemical and physical properties. So we said glass is going to have that kind of silica base, that sand base to it, but they can add different chemicals or elements to the glass to change its properties or change its color. The first glass was produced in Mesopotamia around 250 BC. And then glass making has evolved from there. They figured out how to make it into different shapes to make it clear versus more opaque where it doesn't let light through. They've made it be able to withstand extra heat or impact and things like that. So the first glass that was made was by taking that sand and melting it, which is that silica base. And they would also combine it with ash or soda, which is that sodium carbonate. So that's what most glass was made of. The soda was used to reduce the melting point of the silica. So if you have sand by itself, it has a fairly high melting point. It can withstand a lot of heat. But by mixing it with the soda, it melts at a lower temperature. So when it's heated, it does become molten, where they can pour it into molds and shape it overall. We can also add lime or calcium oxide to glass. This gets added to make the sodium silicate glass insoluble in water. So making sure that the sodium carbonate, that soda, doesn't dissolve. So you can hold liquids in glass for a long period of time without the glass dissolving. Other oxides can be added to modify the properties of the glass. So this is where it may be able to withstand high heats. It may be more shatter resistant and things like that. One example is we can add boron oxide, which increases the temperature stability of glass so it can withstand higher heat. So these types of things, you may have heard of these referred to as borosilicate glass. These are going to be used as ovenware. So like you have casserole dishes in your house or like Pyrex. They tend to be made of borosilicate glass that you can put in the oven. Our lab glassware that would go on top of a hot plate, like our beakers and stuff, are made of that borosilicate glass. That way they can withstand the heat without cracking and breaking. A common additive that isn't used as much anymore due to its toxic nature is lead used to be added to glass. Lead would increase the density of the glass and its refractive index. It would make it reflect more light so that it would sparkle. So if you have older relatives that have like sets of crystal and things like that, it may contain traces of lead to make it have that kind of shine and reflectiveness to it. Glass natural color is going to be a slight green color due to the iron oxide and sand. So glass on its own is a light green color, but we can find glass that is completely clear. It might be more of an orange color, more of a blue color, things like that. How we get the different colors of glass is that small amounts of elements in the glass are added to the glass to influence the color. Some common elements that are used are stuff like selenium, cobalt oxide. Cobalt is going to be more of like a bluish color. Sodium nitrite's used to get more of the clear color. Anything like iron or copper is going to be used to get more of like the orange or amber color, things like that. So they will add these different substances when making the glass to give it those different color characteristics. And whenever we're looking at glass and analyzing it, most glass properties cannot be measured on small fragments of glass. So if you find a tiny little glass shard, it's not going to give you a whole lot of information. So like you might be able to tell the color, but then if it's not the whole piece of glass, maybe it's not a consistent color throughout. You may not be able to determine the full thickness of the glass, its fluorescence, if it glows and reflects light. You may not be able to tell any markings that are on the glass and things like that. So a lot of times we do need larger pieces of glass to get more of the description of where it came from. But there are some things that can be measured on those small samples of glass. The important factors that can be measured on small fragments that can help us identify that glass are going to be density and refractive index. So density we've talked about before, and refractive index we've talked about before. Refractive index is going to be the ratio of the speed of light in a vacuum to its speed in a specified substance. So remember, refractive index refers to how much the light is going to bend throughout that glass or material. We also look at density. Density, remember, is mass over volume. So measure the mass of the glass and its overall volume, and you can figure out the density. This can give us a clue of what elements are used to make that specific type of glass. With the density, we use this to help us find the specific gravity of the glass. This we tend to look at the ratio of the density of the glass, of that substance, compared to the density of water. So look and see, does this piece of glass float in water? Does it sink in water? We can also test it in other materials like alcohol, oil, things like that, to help us narrow down that specific gravity, which is going to be different for different types of glass. So with refractive index, light travels in straight lines at 3.0 times 10 to the 10th meters per second in air, not in empty space, but in air. We said refractive index looks at how much light is bending. So whenever light hits a transparent material, it's either completely reflected and it bounces off, it can be absorbed where it doesn't go through the glass, or it can be transmitted where it will go through the glass. So whenever light passes from one medium into another, so say it passes from glass to the water, which is inside the glass, there's going to be a change in its velocity and the direction of light will bend. So this you may have seen You know, if you put a straw in a glass material, sometimes the straw appears to be in a different location. Or if you've ever, you know, gone swimming, and my little sister used to love to throw toys in the bottom of the pool to make me go get them. Standing outside the swimming pool, the object looks like it is in a different location than whenever you're actually under the water because of that refraction that occurs. Um, so the bend in the direction of light is refraction. And typically, whenever light goes from a less dense substance to a more dense substance, it slows down, which is what creates that impression that light is bending and the object appears in a different location. So refractive index is a physical property. We can observe this without changing the glass itself, and it compares the speed of light in a vacuum to the speed of light within another substance. So with that kind of comparison, that ratio, we can find the refractive index, or RI for short. When substances have the same refractive index, they disappear in one another. So they blend together, and your eyes are not going to be able to detect a bend in that light. So you're not going to be able to see one material within the other. A visible fragment appears to have a halo of light around it, which is known as a Beck line. So when two materials have different refractive indexes, that object is going to be visible. It's going to be outlined, and you'll be able to tell the difference between the two. This is caused by the refracted light rays in a liquid that has a different refractive index than the glass that it is in. And I'll show you the Beck line in a moment. But if the Beck line is on the inside of the object's perimeter, you would need a liquid that has a higher refractive index to be able to identify what the refractive index of that glass is. And like I said, if the refractive index is the same, the Beck line disappears. You don't see that halo around it, and the object vanishes. So with the Beck line, you can see this on the image on the right. It just shows light shining into, it's a beaker with a piece of glass in it. The one on the left, notice that there is no white around the glass object. There is no halo. So this would represent two objects that have the same refractive index, where one disappears within the other. Whereas the two that are on the right, notice that you can see a halo either on the outside of the object or on the inside of the object. That means that these two substances have a different refractive index, so it would be visible. You can see this on the picture on the left that has two beakers. The beaker on the left has a liquid in it, and it has a glass stir rod. Notice if you look through, you can see the glass stir rod below the liquid surface. Whereas the beaker on the right, you know there's a stir rod there, but when you look under the liquid surface, you cannot see that stir rod anymore. That's because this liquid and the stir rod that is in it have the same refractive index. So that stir rod disappears within that liquid. Another thing we can look at with glass is its fracture patterns. This is going to help us figure out what impact was made to a piece of glass. We can determine if glass was broken from the inside or the outside, and it can give us clues about the crime scene itself. So investigators can reconstruct a crime using glass fracture patterns by looking at how the cracks are formed. So we'll talk about this a little bit. There is going to be tension and compression that happens on glass. They're going to cause different fracture patterns. We can look at what shape the fracture is. Is it more in straight lines, or are they more circular? We're also going to be able to tell if the breakage was from the inside or the outside. This is one thing they've seen before where they claim someone broke into the house and stole something, but they find the broken glass on the outside of the house, versus if someone broke in, the broken glass would have gone to the inside of the house. This they've seen in cases of like insurance fraud and things like that. Glass, because it's amorphous and doesn't have that crystalline structure, is slightly flexible. Glass is made to withstand like wind, small impacts, and things like that. But whenever glass reaches its elastic limit, where it can no longer kind of absorb that shock, that's when it breaks and fractures. This elasticity also causes some glass fragments to recoil backwards in the direction of force, which is known as blowback. So this is where even if someone broke a window and the glass fell inside of the house, some of the glass might fall like in their clothing, in their hair, things like that. So we would still be able to tell that they broke the glass. So this could leave glass fragments in the perpetrator's clothing, hair, inside the car, things like that. And whenever a projectile breaks glass, there's two types of fractures that occur in the glass. We have radial fractures that occur and concentric fractures that occur. So I'll draw this in a second. I have a picture of it down below. But whenever a projectile first hits glass, it causes tension on the back side of the glass. So that impact is trying to stretch the back side of the glass where the impact did not occur. This causes compression whenever you are moving out from the center around that point of tension. So this is where we say glass can kind of shock absorb a certain amount, where if a ball hits a window, that shock should move out through the window and hopefully not break it. But if there's too much stress on that window, it will eventually break. So we're going to notice concentric fractures on the same side the force was applied. So if a ball hits a window, the surface the ball hit, that side of the glass will show concentric fractures. Whereas the radial fractures will be on the back side of the glass, on the side of glass that the ball did not hit. So these are caused by different stresses, and they will be a different shape. Concentric fractures are going to be formed by compression, which we said is on that front side. Radial fractures on the back side of the glass are going to be formed from tension, where the glass particles are being stretched apart. So how these look. So notice here we have a piece of glass, applied force, this would be our ball, hitting the glass, causes tension on the back side, which causes a radial fracture. And then on either side, it causes compression on the front of the glass, which is that concentric fracture. So radial fractures are going to be represented as lines. So fairly straight, they might be a little jagged. Concentric fractures, concentric is going to be more of a circular pattern. So looking at our piece of glass on the right, notice that there's an impact in the middle that causes the radial fractures to go out in all directions from that tension. And then going around from that impact site, we're going to have the concentric fractures, those circular ones that occur from the compression force. And you're going to see this moving outward from that impact site. With this, it does create stress marks that are visible at the end of broken glass in an arc shape. So Those conchoidal fractures we talked about, where on this breakage surface, we're going to notice those arc shapes or those rainbow shapes. We can refer to those as stress marks. And there are a couple things we can look at when examining glass forensically. We can actually figure out what projectile was used to create that force. So when measuring the projectile, it's important to remember that the size of the exit hole will be larger than the projectile itself. So if there's a bullet hole in a window, the hole is going to be slightly larger than the bullet is. We can also sequence the fractures. We can tell which fracture occurred first because of those radial and concentric fractures. Whenever a fracture hits something that is already broken, it cannot move past that fracture. So the second fracture will end when it meets lines from the first fracture. So here I just have a couple of simplified bullet holes. So if you notice this first one on the left, I'll just label that number or letter A. It has radial fractures that go out. And excuse my rough drawing skills. Whereas bullet hole B has radial fractures that when they go out, they stop when they hit the fractures from A. So that's how we know that A happened before B, because the fractures from B stop when they hit the fractures from A. We can do the same kind of thing with the bullet holes on the right. Pay attention to where the lines go. So the one on the left has breakage lines that extend all the way out, and they're not stopped by anything. Whereas the second bullet hole has fractures that stop when they meet the first one. So we know that the one on the left had to happen before that middle one. The one on the right has fractures that stop when they hit fractures from the first one and that middle one. So we know that the first shot was the one on the left, second was the one on the right, or the one in the middle, third one is the one on the right. So you can tell that this person, the bullets were being fired from left to right. That is where we are stopping today. And then we will pick up tomorrow with arson.